The next of Martin's principles that we're going to talk about is the Liskov substitution principle. This principle is based on the concept of design by contract that was popularized by Bertrand Meyer. Therefore, before looking at the Liskov substitution principle, we're going to look at the concept of design by contract. Design by contract says that the relationship between a class and its clients, those who use the class, can be viewed as a formal agreement, expressing each party's rights and obligations. When we talk about design by contract in the context of an entire component, it can sometimes get complicated. But if we just focus on how this works method by method, it's fairly straightforward. For example, suppose I have a list class with a method named remove. The contract for the method has a precondition, indicated here by the requires clause, and it has a postcondition, indicated here by the ensures clause. The precondition says that there are certain things that have to be true before this method is called, namely that the index argument has to be within the specified range. Meanwhile, the postcondition tells you what the result of the method call will be, provided that the method was called appropriately. In other words, provided that the precondition was satisfied. The contract part of this also indicate who's at fault if a problem occurs. If the precondition is violated, the client is at fault. If the precondition is not violated and the postcondition is violated, then the implementer is at fault. In the Java documentation for the list remove method, things look similar, but somewhat different. There's no key word for preconditions and postconditions, but the postcondition is simply stated as the main documentation for the method. What was the precondition is now part of the documentation for an exception that is thrown if this condition is not met. This may lead you to wonder if the Java document is a form of design by contract. Well, there is a contract here, but what does it say? In particular, who is responsible for determining if the index is out of range? Is it the client? Is it the implementer? Is it both the client and the implementer? Or is it neither one of them? Please pause the video and try to answer this question. And more important than that, please try to have a good reason for your answer. Ready? If you interpret this Java documentation as a contract, then this contract is saying that the implementer needs to check if the index is out of range. Otherwise, the implementer cannot throw the index out of bounds exception that the contract describes. There's nothing stopping the client from checking the index also, and a diligent client would probably want to make sure that the index is in range so that an exception does not occur. In practice, if an index out of bounds exception is thrown and the program aborts, the client would probably get blamed. Therefore, though the letter of the contract does not obligate the client to check, they probably would. That means that there would be two people checking this condition instead of just one. Let's see what Fowler has to say about this. He says, a precondition is a statement of how we expect the world to be before we execute an operation. We might define a precondition for the square root operation of input is greater than or equal to 0. Such a precondition says that it is an error to invoke square root on a negative number, and that the consequences of doing so are undefined. On first glance, this seems like a bad idea because we should put some check somewhere to ensure that square root is invoked properly. The important question is, who is responsible for doing so? The precondition makes it explicit that the caller is responsible for checking. Without this explicit statement of responsibilities, we can get either too little checking, because both parties assume that the other is responsible, or too much, both parties check. Too much checking is a bad thing because it leads to lots of duplicate checking code, which can significantly increase the complexity of a program. Being explicit about who is responsible helps to reduce this complexity. The danger that a caller forgets to check is reduced by the fact that assertions are usually checked during debugging and testing. I find it interesting that Fowler, who is a big proponent of agile development, seems to also be a big fan of design by contract, and in particular, a big fan of assertion checking. And before we leave the main discussion on design by contract, here's an alternative opinion. Barbara Liskov cautions against partial procedures here. A partial procedure is one that has a requires clause instead of throwing an exception. She says, partial procedures lead to programs that are not robust. A robust program is one that continues to behave reasonably even in the presence of errors. A program like this is said to provide graceful degradation. So Liskov seems to be firmly on the side of throwing exceptions, where Fowler seems to be a proponent of requires clauses and using assertions to enforce them. Why is this interesting? Well, to me, it's interesting because the Liskov substitution principle, which Barbara Liskov created, is based strongly on the notion of design by contract. Okay, enough background and alternative views. What does the Liskov substitution principle say? It says that a subclass should be substitutable for its base class. Or, as Martin says, a user or client of a base class should continue to function properly even if a derivative of that base class is passed to it. Let's look at an example. A caretaker class is using an animal class. At some point, the animal gets hungry and the caretaker has to feed it by calling the eat food method for the animal. There's a precondition on the eat food method that the animal is hungry and a postcondition that the animal is no longer hungry after the method has been called. Based on design by contract, the caretaker is responsible for checking if the animal is hungry before feeding it. Let's assume that there's a method somewhere that allows the caretaker to do this check. After calling the method eat food, the caretaker can be certain that the animal is no longer hungry. Now, what if the particular animal that the caretaker must care for is a cat? From the point of view of the caretaker component, this information may not be known. Therefore, it's necessary that the cat behave like an animal. In particular, if the caretaker feeds the cat, it should not be hungry afterwards. Even though the postcondition for the cat has an extra condition, namely that it eats cat food, part of the condition needs to be that the cat is no longer hungry. So what's the problem? Well, now suppose we have a screen class that uses an ellipse object. At some point, the rectangular screen changes the size of the ellipse to match its width and height. Let's say that the screen's width is 640 and its height is 480. There is no precondition for set size, and based on the postcondition, after the call, the ellipse will have a width of 640 and a height of 480. Now suppose that circle is a subclass of ellipse. Circle has a quite reasonable precondition for set size. It says that the width must equal the height. After all, if they were not equal and they changed accordingly, we wouldn't have a circle after the call. What effect does this have on the screen class? Well, it turns out to have a very bad effect. The screen class thinks it's dealing with the contract for an ellipse, so it calls set size with 640 and 480. This, in turn, violates the precondition of circle, and there's no telling what might happen in that case. Perhaps an exception will be thrown and the program will abort, or perhaps the height parameter will be ignored and the circle will get a height of 640. But in that case, the implementer of the screen component has incorrectly assumed that the ellipse's height is 480. So this is a problem. The subclass is causing the user's class to behave improperly, and therefore a circle object cannot be substituted for an ellipse. In terms of contracts, the Liskov substitution principle is violated if the subclass method makes itself harder to call than the superclass method, or if the subclass method does less than the superclass method after it returns. In the circle example, the circle put more constraints in the precondition. The ellipse didn't have any constraints. In the cat example, the cat guaranteed more than the typical animal, but it also guaranteed what the typical animal guaranteed, that it was no longer hungry. Since the Liskov substitution principle is about specifications, preconditions and postconditions, it can be difficult sometimes to see that you have a problem. We want to be able to extend classes instead of modifying them in accordance with the open-closed principle. But extending classes in a way that violates the Liskov substitution principle could force us to end up violating the open-closed principle. For example, if we spend a lot of money creating the circle class and we can't really afford to change it, we could always modify the screen class, the user class, so that if the ellipse happens to be a circle, we do something else. But modification of the screen class directly violates the open-closed principle. That's why Martin says that violations of the Liskov substitution principle are latent violations of the open-closed principle.